Hey guys, this is the fourth video in chapter 10, the video about partial pressures. So partial pressures kind of follow Dalton's law. Dalton's law states that the total pressure of a mixture of gases is equal to the sum of pressures that would exert if it were present alone. What that means is that the total pressure of a system is equal to all of the partial pressures for each individual gas. For a mixture of gas, say 50% helium and 50% oxygen, if the total pressure was 500, that means each gas would exert a pressure of 250. It's directly proportional to how much is there in moles, of course. It's kind of cool because we've seen from the ideal gas law that pressure and moles are the same, or not the same, but they're related. And of course, this mixture is in the same volume and the same temperature. And so what we find is that the total number of moles the total pressure and the partial pressures are equal to, or proportional to, the number of moles present and something called the mole fraction. For example, here we have a bunch of mixtures of gases. What we can see is that we've got some mixture here. Okay, each of these mixtures is equal to 1 atmosphere, but each one is composed of a small amount of different gases. So this gas here is 20% argon, 30% helium, 50% oxygen by molar percentages. And so the gas itself, the pressure, total 1 atmosphere, would be 0.5 atmospheres of oxygen, 0.3 atmospheres of helium, and 0.2 atmospheres of argon. What those percentages are called, or if they're expressed as decimal, those are called mole fractions. Okay, mole fractions. And so we've got a couple things here. The mole fraction of a gas is equal to the partial pressure of the gas over the total, or the number of moles of the gas over the total number of moles, because both of those things are related through the ideal gas law, right? This RT over V here remains constant. So all that we're left with is this N of gas over N total. And that's the mole fraction. It's a decimal. You can multiply by 100 to get mole percent if you wanted to. But the point is that if we want to figure out the partial pressure of a gas, all we have to do is multiply the total pressure by that mole fraction. And we can do the same thing for the number of moles. Let's take a look at what this looks like mathematically. Here we have an example of 13.4 grams of methane and 22.7 grams of ammonia at 298 Kelvin is held in a 4.3 liter container. We want to know the partial pressure of each gas and the total pressure. So what we're going to have to do is we're going to have to solve the ideal gas law a couple times, one for each one, and then add them together. And I'm going to show you that the percentages from the pressures are the same as the percentages from the number of moles. So to start off with, we've got 13.4 grams of methane that we have to convert into moles. And same thing for ammonia. We got to convert that guy to moles. That's 17 grams per mole. When I do that for methane, I get 0.8375 moles. And when I do it for ammonia, I get 1.385 moles. I know that's not correct significant figures, but I'm just trying to prove a point here. Now if I add up the total number of moles to get the total number here, I get 2.2222 moles. Now what I'm going to do is I'm going to divide each of these by the total to get the percent, just to show you that moles and pressure are mathematically related. Let's take 0.375 divided by 2.222, and I get, and multiply by 100 of course, and I get 37.7%. So this mixture is 37.7% methane by molar amounts. And that means it's 62.3% ammonia. All right, now we'll come back to that just to show you that those things are related. Now let's do the ideal gas law, one for each one, to figure out the partial pressures, or just the pressure of each individual gas. So PV equals nRT. We want pressure. We're in a 4.3 liter container. The number of moles for methane was 0.8375 N, and then R 0.08206, and then T 298 Kelvin. We're going to do the same thing for ammonia. Pressure, volume's the same. My moles here, 1.385. My R, and my temperature. I can plug that in the calculator and solve for the two different partial pressures. So when I do that for methane, looks like I get 4.76 atmospheres. When I do this for ammonia, I get 7.87 atmospheres. So those are the partial pressures. My total pressures here are going to be 4.76 plus 7.87. And I get 12.63 atmospheres as my total. Now if I did the percentages, so what I'm going to do is I'm going to take 4.76 divided by 12.63 times 100 to get my percentage of methane and ammonia. So 4.76 divided by 12.63, and I get 37.7% methane and 62.3% ammonia. It's kind of cool because you can actually see mathematically that both the molar percentages up here and the percentages of the pressures are equivalent. That's because they're related through the ideal gas law. Anyway, that is it for partial pressures. Hopefully that made some sense. And then I'll see you in the last video where we talk about the rest of Chapter 10.